Welcome to the Senior Design 2 final presentation called the Digital Pixel Helmet Platform. Our advisors are Dr. Chan from Senior Design 1 and Dr. Wei from Senior Design 2. These are the team members of Group 9. Hi, my name is Joshua Soriano and my major is electrical engineering.
I'm Vince Doe. I'm an electrical engineering major.
Hi, I'm Devin Schuck-Snyder, an electrical engineering major.
I am Ryan Hauk, and I am an electrical engineering major.
The Digital Pixel Helmet Platform is a wearable entertainment system centered around a programmable LED display. It combines an embedded controller, on helmet user inputs, and wireless communication with a companion application. These elements work together to control the helmet's visual output as one integrated system. The background for DPHP comes from performance helmets that use lighting as part of their artist's visual identity. Daft Punk showed that a helmet could become more than just part of a costume by combining music, visual design, and technology into one recognizable experience. This inspired our team to explore how modern embedded systems, programmable lighting, wireless communication, and custom electronics could be integrated into a wearable platform. The project also gives us the opportunity to combine several areas of electrical engineering into one complete system. We divided our goals into basic, advanced, and stretch categories. The basic goals focus on the core helmet functions, including programmable visuals, on helmet controls, wireless operation, sound reactive feedback, rechargeable power, and secure app access. The advanced goals expand on the user experience through the greater app control, custom text, more complex animations, adjustable visual settings, and more flexible touch inputs. Finally, the stretch goals include user uploaded content and an internal cooling solution, as well as a visual aid system to improve awareness while wearing the helmet. These objectives turn our project goals into specific engineering tasks. For the basic system, that means designing the LED hardware, integrating the touch and microphone inputs, establishing Bluetooth communication, and implementing charging, battery monitoring, and access control. The advanced objectives focus on expanding the firmware and apps so users can control text, animations, audio reactive modes, colors, and touch commands. The stretch objectives are tasks that require additional development and feasibility testing.
This slide shows the main specifications and requirements that our design is being measured against. The highlighted rows are the specifications we plan to directly demonstrate during the final presentation. The first requirement is helmet response time. We are aiming for an upper limit of about 5 seconds for startup time. The second requirement is for capacitive touch response time. We are aiming for it to be less than 1/10 of a second so it is responsive and snappy for the user. Finally, the third requirement is for microphone SNR. We are trying to have the SNR be as good as possible so the microphone has the best range and most accurate input. So we want it to be at least 40 decibels. The non-highlighted rows still matter for overall design, but the highlighted specifications are the one we are prioritizing for live demonstration and verification. Our block diagram shows how the subsystems interact. The 12-volt battery supplies power and is rechargeable through a barrel jack port. We use a charge controller to safely modulate the power coming into the battery. The battery powers a 3.3-volt buck regulator, which powers the ESP32, the microphone, and the capacitive touch IC. The battery also powers a 5-volt buck, which powers the LED peripherals. Our app, which can be downloaded onto mobile smartphones, communicates directly with the ESP32. Additionally, the capacitive touch, after receiving input from the electrodes, transmits data via I2C to the ESP32. The microphone converts audio to a digital signal via I2S, which is also sent to ESP32. The ESP32 sends its commands via the NRZ protocol to LEDs, which is converted from 3.3-volt to 5-volt logic by our level shifters.
This diagram shows the main power flow through our helmet. First, power enters through the barrel jack port and goes into the charge controller, which manages charging for the 12-volt battery pack. The battery output then passes through a fuse before splitting into two regulated rails, a 5-volt rail and a 3.3-volt rail. The 5-volt rail supports the LED system, while the 3.3-volt rail supports the MCU, capacitive touch, microphone, and communication circuits. For our 12-volt battery, we selected the CMP54A4537 because we need a portable and rechargeable power source that can fit inside our helmet. Next, for our charge controller, we chose the LTC4011 because it supports our 12-volt battery and handles about 3 amps of programmable charge current and does not require an external MCU, which keeps the charging design simpler and more reliable. For our charge controller schematic, we used the datasheet's typical application as reference when designing the schematic. For our charger PCB, the layout places the components in one organized board so the helmet can recharge safely and supply power to the rest of the system. Next, we chose the LM2576 for our 3.3-volt buck switching regulator because the MCU, capacitive touch module, microphone, and other logic circuits need a stable 3.3-volt supply. Lastly, we chose the LM5117 for our 5-volt buck switching regulator because the LED subsystem requires a high current demand. The LED matrix visor, LED ears, and battery indicator all depend on a stable 5-volt power. For our 3.3-volt and 5-volt regulators, we use Webench to generate our power design schematics. We chose an MCU because it has enough processing power for LED control, Bluetooth communication, touch sensing, and microphone input, while still keeping cost and power consumption low. An FPGA or MPU would be more powerful, but they would add unnecessary complexity for our system. We chose the ESP32 as our MCU because it gives us strong processing power, built-in Bluetooth low energy, and it can handle LED control, app communication, and sensor inputs without needing extra wireless hardware. Furthermore, we designed our MCU board so it can connect to our USB programming circuit, receive sensor inputs, and send data to our peripherals. This MCU PCB is the main control hub for our helmet.
Here's the capacitive touch architecture. It is powered by 3.3 volts from the regulator. Then the IC itself provides current to the electrodes. When that current is disrupted, a touch is registered and the IC sends the data to ESP32. We selected capacitive touch sensors because they have no moving parts, support multi-touch gestures, and are more reliable than traditional buttons. This lets us create a clean, hidden interface that blends naturally into the helmet. We chose the MPR121 because it supports up to 12 touch inputs, communicates through I2C, and offers programmable sensitivity. This gives us flexibility to recognize different touch gestures while leaving room for future expansion. Here is the PCB layout for the capacitive touch module. The board is compact enough to fit inside the helmet while still providing easy integration with the touch electrodes and the rest of the system. The capacitive touch system provides local control of many helmet functions without requiring the mobile app. When an input is detected, our code differentiates the type of input according to the acceptable inputs we have programmed. For the microphone architecture, power is delivered by the 3.3-volt regulator, and the mic takes in audio input. Via I2S, it takes the audio and translates it into a digital signal, then sends it to ESP32. We selected a digital MEMS microphone because it provides a digital output directly to ESP32, which simplifies our design, improves noise immunity, and eliminates the need for extra circuitry. We chose the SPH0645 LM4HB because it offers a good signal-to-noise ratio, low power consumption, I2S communication, and reliable availability. It gives us clean audio input while integrating easily with our ESP32. For the microphone subsystem, we had several issues with the I2S microphone, most of all it being hard to solder. Therefore, with Dr. Wei's permission, we switched to using a Max 9814 audio amplifier breakout board with an electret microphone. This schematic shows the microphone subsystem, and for the PCB, it was designed to follow the manufacturer's layout recommendations for this specific family of MEMS microphones. After being powered on, the microphone starts taking an input, but only when the mic mode is selected via the capacitive toucher app does a digital signal output get sent to ESP32 and then displayed on the LED matrix.
This diagram shows the overall architecture of the LED subsystem. The ESP32 sends separate NRZ data signals to each LED PCB, where a level shifter converts the 3.3-volt logic into a 5-volt signal that the LEDs can reliably read. The visor, ear assemblies, and battery indicator are all powered from the same 5-volt rail, while each board keeps its own level shifting and LED driver path for more reliable control. We compared discrete RGB LEDs, addressable RGB LEDs, and pre-built matrix modules. Addressable LEDs were selected because they use a single data line, include integrated control per pixel, reduce routing complexity, and still allow the custom PCB shapes needed for the helmet. We compared three addressable LED options. The SK6812 Mini E was selected because its smaller package supports a denser custom PCB layout while still providing the required 5-volt operation, single wire control, and adequate refresh performance for the helmet. This representative schematic is reused across the visor, side panels, and ear PCBs. It includes level shifting, data protection, local decoupling, and the series connected LED data path. The visor PCB contains the main LED matrix and was shaped to fit behind the helmet visor while supporting the required LED density and visibility openings. The left and right panel PCBs use mirror custom shapes to fit beside the visor and provide a synchronized accent lighting on both sides. The ear PCB uses a circular layout so it fits inside the ear housing and creates an evenly distributed LED ring effect. The battery indicator circuit uses level shifting, data protection, and filtering to reliably control the rear 6 LED strip from the ESP32. This compact PCB connects the MCU to the rear LED strip and clearly separates the input and output connections for easier assembly and testing. Due to JLC PCB having delays on the LED subsystem PCBs, we decided to add a new subsystem, the audio amplifier, using an LM386. This audio amplifier subsystem will be designed to be integrated with the capacitive touch. Each action with the capacitive touch makes the speakers connected to the LM386 play an audio file respective to the action, so the wearer knows what the LED matrix action is taken.
This is the software flowchart for the entire project with functions from both the helmet and app. Once the helmet is turned on and its peripherals are initialized, it is prepared for the app to connect with it, though it can still function on its own with the capacitive touchpads. While connected, the two devices regularly update each other on their current states, and the app is able to perform more advanced actions to customize and navigate through the helmet's various display modes and the presets within. Upon disconnection, the helmet will still function once again through the capacitive touchpads, albeit with lesser control. The C language was chosen for programming the helmet's MCU software because it has the most straightforward language for this role. It has direct access to the built-in C APIs for the ESP32 and in general has the simplest integration with its firmware. Flutter was chosen to be the programming software for the companion application. Flutter's programming language is Dart, based around object-oriented programming languages like C# and Java, which the app lead has the most amount of experience with. Flutter also contains a unified codebase, robust widget library, and streamlined plugin support for a high-performance user interface. Flutter is also compatible with Windows, iOS, and Android platforms, making it highly adaptable for future development. Bluetooth Low Energy was chosen to facilitate the wireless communication protocol between the helmet and app because its data transferring capabilities are adequate for the project's scale while being more energy efficient and simple to set up compared to Wi-Fi. For the ESP32, Bluetooth is implemented through the Nimble stack for its low demand on the MCU's RAM and flash memory. For the app, Bluetooth is implemented through the Flutter Blue Plus plugin for being the most established and well-developed package for Bluetooth, especially for future mobile phone applications. The companion app follows the MVVM software architectural pattern as seen here. The pattern divides the code of the application into three distinct layers: views, view models, and models. The views contain the elements of the app that the user regularly interacts with, which is the app layout and interface. View models contain the logic for updating the user interface, whether from user input or updates from the helmet. The models handle the core logic of the app, which is the communication protocol with the helmet and the protocol for sorting and handling presets.
This slide shows how the helmet is designed to support the electronics internally. The 3D printed shells provide space for wiring, foam padding, and modular PCBs, while the smoked visor hides the LED matrix when powered off. Separate internal cavities also improve mounting, organization, and access during assembly and testing. This side view shows how the ear assembly combines visual output and local user control. The circular LED PCB sits inside the ear pocket, while a frosted acrylic ring diffuses the light and hides the board. The center touchpad allows the user to change presets and basic functions without opening the mobile app.
For our testing plan, we first tested each peripheral separately, then integrated the full system and tested everything again. We used our custom ESP32 PCB, a digital multimeter, and an electronic load to verify the hardware. We also tested the companion app as both a web and Windows application, including Bluetooth connection and communication. For our 3.3 volt and 5 volt regulator testing, we use an electronic load equipment to verify that the regulators can handle a load current of 2 amps by incrementing the load current by every 0.5 amps in a range of 0.5 amps to 2 amps. For our MCU testing, I use a multimeter on the chip's input voltage pin to ensure that it is stably receiving power from the 3.3 volt buck regulator. For the battery and charging test, we connected the wall adapter to the charge controller. We verified charging through the icon in the companion app and a status value of 2 in the VS Code terminal. We also compared the app's battery percentage with the indicator LEDs and the battery voltage measured using a multimeter.
For LED testing, we used the Wesiri 8x32 LED matrix as a substitute for our custom PCB. Although the pre-built matrix uses WS281B LEDs, these types of LEDs are programmed and perform in similar ways to the chosen SK6812 Mini E LEDs we chose for this project. We also have Sparkle I/O pre-built LED rings located in the ears that are always going to be set to rainbow mode. We tested the capacitive touch subsystem using our final custom PCB containing the MPR121 capacitive touch controller. We used a copper foil sheet from Adafruit to cut out 2 electrode panels for our electrodes. We successfully implemented tap and hold gestures, confirming that users can navigate presets, switch modes, and activate the battery indicator. For the microphone, we used a third-party breakout board with a Max 9814 audio amplifier and an electret microphone. Initial audio readings were noisy, so we introduced some software techniques on the microphone and LED visor to display the sound better. These improvements produced a much cleaner response, allowing the visor display to react smoothly to ambient sound and speech. To validate the battery indicator, we used a variable laboratory power supply, the NGE100, to simulate different battery voltage levels for a simple 6 LED strip. Some of the results are shown here. After individually testing each part of our helmet, we connected every part together for a fully integrated test. We were able to confirm successful power flow to all parts due to the LEDs on the breakout boards, LED strips, and LED ears working. We also implemented controls via our final capacitive touch board and implemented sound to announce mode and preset changes with the speaker. The helmet starts in demo mode, where it cycles through text, static images, and animation presets. There are 6 modes: demo mode, text mode, graphics mode, animation mode, sound mode, and group mode, which all have multiple presets. For the capacitive touch, the left electrode goes to a previous preset and the right goes to the next. Holding for 2 seconds changes the mode, except for mic mode, which can be entered into by holding either electrode for 4 seconds. Lastly, holding both touchpads for 2 seconds activates the battery indicator LED strip, which shuts off after 3 seconds.
Here are the current states of all 7 screens tested for the app layout. The user interface is developed such that the user can navigate through all the screens, select the specific display mode of that screen, cycle through presets and groups, change the color from a color slider, save, name, and load those colors, and select specific presets and groups from a drop-down menu. Several other planned features have been designed but are currently inert. Changes made to each screen are always retained as the user navigates between them. To test the handshake, an ESP32 dev kit standing in for the helmet was configured to be a BLE server, and the app was configured as a BLE client. The server would advertise itself through Bluetooth until the client would scan for it and connect to it with a simple pairing. The BLE presence and the handshake process was confirmed through the light blue app, Arduino IDE serial monitor, and VS Code debug console. This led to further development with the app connecting to the final design's MCU. With the MCU and app connected, the communication protocol was developed for both ends of that connection. Simple passkey authentication is used alongside encryption for security. BLE characteristics are used to exchange data between the two devices with notifications and writes without response. The different features from this exchange can be seen here. To summarize, the helmet's hardware, software, and application have been tested and confirmed for full functionality. The ESP32 MCU software has been uploaded successfully, and it can communicate with the other peripherals, including the app, through Bluetooth. The power system was integrated and proven to be able to power the other peripherals with adequate power. The microphone and capacitive touchpads were able to receive input from the user, while the LED matrix could output several different display modes while the speaker informed the user. The app was successfully created and interacted with the helmet. The project underwent several challenges throughout development, some of which fundamentally changed the plan for creating it, such as the speakers replacing the LED subsystem, the microphone being replaced by a dev kit, and the programming language and IDE for MCU software changing. All were addressed and rectified to create the project seen now. The budget and bill of materials for the major components of this project is shown here. The overall budget is about $1,600 allocated to the various subsystems of the project, as well as the shell of the helmet, core control unit, and PCB components. The total cost of these components amounts to about $840, which was further increased by the PCBs for the LED subsystem, which could not arrive in time. Even so, it unfortunately increased our costs slightly over budget. Here is the work distribution for all team members. Joshua Soriano is the overall lead and spokesperson for the entire project, as well as the lead for designing, building, and programming the LED matrix visor. Vince Doe is the lead designer for the power supply unit and main PCB. Ryan Hauk is the lead designer and programmer for the companion app and Bluetooth protocol. Devin Schnecksnyder is the lead for designing and building the audio system and capacitive touchpads. We also have secondary roles to aid the leads and compensate for absences. As of this presentation, progress on the project has resulted in full functionality for all of its peripherals: the app, power system, capacitive touchpads, microphone, LED matrix, communication protocol, and the additional speaker subsystem. The project has been successfully contained onto the backpack and the helmet. For future development, there are several considerations to make this project better. The basic developments are integrating the LED subsystem and the non-required goals for the companion application. Far greater developments would include the cooling system and the PCB redesign for greater compactness.
These are our references used for this presentation. And thank you for watching.